So for this session, we'll be discussing double integrals in rectangular coordinates. So I assume that you have watched the associated lecture videos. So it's section 2.4 and 2.5. So in 2.4, it's double integrals in rectangular coordinates. And the domain or the region is a rectangular region, while for 2.5, the region is more general. Okay, so I have prepared some examples here and I'll give you the solutions. So if you have questions, you can ask them and then I'll try to answer them. Let's start with our first problem here. So we want to evaluate the iterated integral from 1 to 2, integral from 0 to 1 of 6x y squared dy dx. So in here, this part here, it's in terms of y. So we are going to consider x to be a constant. So we are integrating with respect to y. And then after integrating with respect to y, we'll be left with some expressions in terms of x only, and then we can integrate with respect to x afterwards. So here we have this as our original expression, and then here we just put our grouping. So we have this inside integral here, the inner integral from 0 to 1, 6x y squared dy. So if we integrate that with respect to y, take note, with respect to y, we will have here y cubed over 3, but we have here 6. So 6 over 3, that's your 2 here. So we are evaluating this expression from y equals 0 up to y equals 1. Okay? And we will be left with the integral of 2x dx from 1 up to 2. Okay, so for this part, again, we integrate now, this time with respect to x. So we will have x squared, and we are evaluating from x equals 1 to x equals 2. So notice in here, I specified clearly what the variable is. Okay, in here, since it's really obvious that this is already in terms of x, we don't have to put x equals 1 or x equals 2. Since there's only one variable here anyway. And therefore, if we do the integration, we'll end up with 4 minus 1, and this is equal to 3. Okay? So it's straightforward computation. Okay? You have the inner integral, and then you integrate that with respect to the variable in that inner integral, holding the other variable constant. Then afterwards, after integrating, you now follow that up with the integral of the next variable. So in here, if you look at this, we have integral from 1 to 2, integral from 0 to 1, 6xy squared dy dx. For this next example, I'll interchange the two expressions. Okay? So in here, we will have the integral from 0 to 1, okay? Integral from 1 to 2, 6xy squared dx dy. So if you look at this expression here, we will have integral from 1 to 2, 0 to 1, we have the function, and then dy dx. This time, we interchange the two integrals, okay? And of course, if we interchange the integrals, we are also interchanging here the variables. So for this one, we will have this time, this is our inner expression here. So we have this expression here. So we are integrating with respect to x. So this time we are holding y as a constant. So if we integrate, we will have 3x squared y squared. So of course, integral with respect to x, this is x squared over 2, but you have 6 in here, so that's your 3. and your y squared is held constant, so it remains as y squared. And since we are evaluating or we are integrating with respect to x, we just emphasize that this guy here, we are substituting x equals 1 and then x equals 2. Okay? Or we are evaluating from x equals 1 to x equals 2. So after evaluating x equals 1, x equals 2, we end up with 9y squared. Okay? So we integrate this 9y squared from 0 to 1 with respect to y. Okay? So after integrating, we will end up with 3y cubed, and we are evaluating from 0 to 1. So just like before, in here I specified the variable x equals 1 until x equals 2. In here, there is no need to specify because we only have the variable y here. So if we evaluate from y equals 0 until y equals 1, we will end up with 3. So notice this guy here, it's equal to 3. And if we do the interchanging of variables of integration, the answer is also 3. And that is possible. It is expected that they will have the same answer through Fubini's theorem. So if your limits of integration are both constants, okay, for both integral, then you can just interchange the integration, okay, with respect to x or with respect to y. And the results should be the same. Okay? So that's for the first two problems. Questions? For the next problem, we want to integrate over the region R, y sine xy dA, where r equals 0, 2, cross 0, pi. So in this notation, we expect that this part here refers to the variable x or the x-axis, and this guy here refers to the y. Okay? So your region is from 0 to 2, cross 0 to pi. So in order to evaluate this, okay, first we try to observe the integrand. So you have to choose which variable you use first. So which variable will be the inner integral, okay? If you look at this, you have y sine xy dA. So if you integrate with respect to y, then you are integrating y sine xy. And you can use maybe your integration by parts, particularly Liate, if you are integrating with respect to y. Okay? But if you do that, of course, the solution will be long if you use your variable y as the first or as the inner variable of integration. So instead of using y, if, however, we use x, then y will be held constant, then, you can easily integrate sine xy with respect to x. Because y is just constant, and here you just have a y, which is constant relative to x. So we set this up, okay? We set this up in the following. So we integrate y sine xy. We start with the dx, and then later the dy. So if we are starting with the dx, you take note that in this region here, this is for your variable x, this is for your variable y. So you start with the variable x, you have to put also the limits of integration for the variable x here, which is 0, 2. And then for this guy here, of course, that's for the variable y, which is 0, pi. So in this form, we integrate with respect to x. You can, this is sine xy. There's a y here, so you can let say u equals xy, du will be y dx. So you are integrating with respect to x. Okay? But anyway, after integrating this with respect to x, you will get this negative cosine xy. And you are evaluating from x equals 0 until x equals 2. Okay? Questions at this point? So everyone got this. Y sine xy. You integrate that with respect to x. That will be negative cosine xy. So evaluating at x equals 0 until x equals 2, we will have cosine 2y. So that's for x equals 2 plus negative. So you have your negative cosine 2y plus negative of cosine 0. That's for x equals 0. But cosine 0, that's equal to 1. So we'll just have here negative cosine 2y plus 1. And then we are integrating this with respect to y over the interval now 0 comma pi. So if integrate with respect to y, we'll end up with negative sine 2y over 2. That's for this one. And then plus y, that's for this one. And then we evaluate from 0 to pi. Okay, from 0 to pi. So in here, you will get sine 2 pi, that's equal to 0. Also, sine 0, that's equal to 0. So this guy here will disappear after evaluation at y equals 0 until y equals pi. On the other hand, for this y here, you'll just have pi minus 0. So the final answer, that's equal to pi. Okay? Now, the region, it's just a rectangle. Okay? So, like I said earlier, you can use Fubini's theorem. So you can interchange the two here. Okay? But of course, the solution will be longer because you need to use what? Integration by parts. But that's still possible. And when you do that, you should get equals pi. So if you have the freedom to choose which variable to use first, then choose the easier one or the expression at least with or the variable with easier integration. Okay? Questions? For our next problem, we want to find the volume of the solid S bounded by the surface 4x cubed plus 3y squared plus z equals 20 and the planes x equals 1, y equals 2, and the coordinate planes. Okay? So, we let S be the solid under the surface. Z equals 20 minus 4x cubed minus 3y squared. So, we can consider this as the function f of xy. Okay? So, this is the surface for this. Okay? And then you have x equals 1. So, if you look at this, this is the point, this is the origin. Okay? So for the y, it's going that direction. That's why you see y equals 0.5, y equals 1, y equals 1.5. In here, you will have y equals 2. Okay? And then for this guy here, you see this x equals 0.25. And then for this guy here, this is x equals 0.5. And then for this part here, that's your x equals 0.75. And then here, of course, that's your x equals 1. So don't be confused. This is your origin here. That's where your origin is. Okay? So the region, it's a rectangular region. You want x equals 1 y equals to, and then the coordinate planes, it means x equals 0 and y equals 0. So your region here, it's rectangular. It's the rectangle 0, comma 1 cross 0, comma 2. So this is the 0, comma 1. That's for your x. And then 0, comma 2, this is for your y. And therefore, the region, okay, the region will be this part here. That's the domain that we are considering. Okay. And then, of course, if we want the volume of the solid, then this is given by this double integral. The volume of S, it's the double integral over the region R of this function here, 20 minus 4x cubed minus 3y squared dA, where A here, it's of course the area of the region. Okay? But we translate this into rectangular coordinates, okay? Which means in terms of dx and dy. And this guy here, you can write that as the integral, okay? From 0 to 1, 0 to 2, okay? So I think I should read this as the integral from 0 to 2 of the integral from 0 to 1, 20 minus 4x cubed minus 3y squared dx dy. Okay? So in here, my first variable will be the dx. So the inner limits of integration should be the interval for x, which is 0 to 1. And then the outer variable here, it's your dy. So the outer limits of integration should be for the variable y. And you can also interchange this. You can do dy dx. And of course, you have to interchange these two. And the difficulty, it's the same. I'm saying that because, well, this is just a polynomial expressions in terms of the variables x and y. And polynomials are easily integrable. So you can interchange the two guys here and the two guys here, and you will still get the same final answer. So anyway, we'll be doing this ordering, the dx first, and then after we'll do the dy. So if you do this, we will have 20x. Here you have x to the 4 over 4, but you have negative 4 here, so you'll be left with x to the 4. And then here, 3y squared is constant, so you'll just have to add that x there. I mean, to multiply that x there. And you are evaluating from x equals 0 until x equals 1. So after evaluating, we will only have 19 minus 3y squared. Okay? So now, we integrate this with respect to y from 0 to 2. So if we integrate this, we'll only have 19y minus y cubed. So coming from here, it's 3y cubed over 3. That's why we only have y cubed here. And then, finally, we evaluate from 0 to 2. We'll have 38 minus 8, or this is equal to 30. Okay? Questions so far? Okay. For next problem, we are now going to consider what we call the type 2 integrals. So the region, okay, the domain of integration, it's no longer rectangular. So in here, we want to integrate from 0 to pi over 3 of the integral from 0 to cosine y, x sine y, dx dy. So notice in here, variable dx first before variable dy. So this means this guy here, these are actually x equals 0, and then here you have x equals cosine y. So if you look at if we look at the integral, the domain of integration, you have from x equals 0 to x equals cosine y. Okay? The graph of x equals cosine y is what? We have here x equals cosine y. So this is not a function, but it's like this. Okay? Okay? So this is your x equals cosine y. Okay? No, that's not it. When y equals 0, x will be equal to 1. So that's not it. The graph is something like this. Let me change that one. So when x equals when y equals 0, x will be equal to 1. So it's from this. And then when y equals pi over 2, x will be 0. So you have this. Okay. And then when say x, anyway, we just need until pi over 3 here. So 0 to pi over 3. When y equals pi over 3, what is cosine of pi over 3? So suppose this is your pi. Suppose this is your pi. Y equals pi. Pi over 3 is somewhere here. Okay. So when y equals pi over 3, cosine of pi over 3, that's 1/2. So it's somewhere here. Okay. So the graph will be, you have something like this. Okay. So you look at the graph of y equals cosine inverse of x. Let us try to recall the graph of y equals cosine inverse of x. Okay. So somewhat like this. So what is this? We have from x equals 0 up to cosine y. So this is for the variable x, correct? From x equals 0, again, this is your x-axis, this is your y-axis, okay? And then this part here, this y, this strip here, okay, this strip here will run until y equals pi over 3. So if this is your pi over 3, this will be the region. Okay? Hello? So this will be the region. So if we have that, okay, let us do the integration. Observe that if we do the integration with respect to x, you have only here x. Sine y is constant. So we can easily integrate this with respect to x. So this will be, we integrate with respect to x. So this guy here, we start with respect to x. This is x squared over 2. That's why we have it here. And then we evaluate from x equals 0 until x equals cosine y. And therefore, we will end up with 1/2 cosine y squared sine y. And then we integrate this with respect to y from 0 to pi over 3. And notice this, this is trigonometric integral, so you can do all the techniques that you know. Anyway, this is easy. You can just let u be equal to cosine y. Du will be negative sine y dy. So this is easily integrable. Okay, just try to recall your trigonometric integration. So you will end up with negative 1 over 6 cosine cube y. And then you evaluate this from y equals 0 until y equals pi over 3. Okay? And then again, when y equals pi over 3, cosine pi over 3, that's 1/2. And then you cube that. Okay? And then you have cosine 0, that's just 1. So in here, we will end up with negative, we will end up with 7 over 48. Okay? So how is that? You will have negative 1 over 6 times at pi over 3, that's 1 over 8. Okay? Cosine of pi over 3, and then you cube it. Then here, minus 1. So this is equal to negative 1 over 6 times negative 7 over 8. That's why we have here 7 over 48. Okay? Questions for this? Now, if you intend to change this, to interchange the variables, you will have to check the proper limits of integration. Of course, you cannot just change this. You cannot just change 0 to pi over 3, 0 to cosine y. You will have to change the integral, the limits of integration properly. Okay? So if we actually do that, so again, if you try to do that, you will have your function. So this is your pi over 3. This is your 0. Then that's your 0. And at cosine 0, at x equals 0 in here, take note, x equals 0 until x equals cosine y. So you will need the function, again, it's x equals cosine y, or your y equals cosine inverse of x. Okay? So for this, again, from 0 to pi over 3, you have here your 1/2, and then you have here your 1. Okay? At you have this point, and then you will have this point here. Okay? At y equals 0, x equals 1. At y equals pi over 3, x equals 1/2. So you will have the part of the graph in here. Okay? You will have the part of the graph in here. Okay? This is your y equals cosine inverse of x. So this is the region. Okay? So this is the region of integration. This is a straight line, and then this is curvy. Okay? So if you want to change, you want to do dy first. Okay? You want to do dy first before dx. So you need the values for y. It will be from this point up to this point, but your x will only run from x equals 0 until x equals 1/2. Take note that here, the upper limit will be pi over 3. That will be pi over 3. So if you only consider this part here, that's rectangular. This guy here, it's rectangular. So you will have something like integral from, so you do dy first, integral from 0 to pi over 3, okay? And then you integrate from 1/2 or from 0 to 1/2, okay? So you will have here the function, and then you have your dy over dx. But you have not considered this part yet. So you will have the plus, okay? And then you will have your dy, again, dy, and then, so dy here, and then the dx here. So this time for the dy, for the second part, it will be from 0, okay? That becomes from 0 in here until this point, which is your cosine inverse of x. Correct? So in here, it will be from 0 to cosine inverse of x, and then your x will run from 1/2 up to 1. So this is 1/2 up to 1. So if you try to interchange the variables of integration, you can do that. But sometimes the integrals become harder or become more complicated. Like this one, you have to divide into 2 parts. Correct? So the moral of the story is you choose which order is better, or at least it's easier to calculate. Okay? By the way, just a disclaimer. This part here, I know I said it's cosine inverse. So y equals cosine inverse of x. So this, try to recall the correct graph for the cosine inverse. If it is like this, then that's good. If not, it's still, you need to draw the graph properly. Okay. So anyway, let's move to our next problem. So in here, we want to integrate from 0 to 1, then from negative x to x squared, the function y squared x dy dx. So in here, the variable of integration first is ty. Therefore, this guy here, it's with respect to y. And obviously, it's with respect to y because you have here minus x and then here x squared. Okay? So it's your y equals minus x, y equals x squared. And then your x will run from 0 until 1. Okay? So this is our problem. Suppose no, we are interested with the region itself. So if you try to graph this, you have here, first, you have your y equals negative x, and then the other one, you have your y equals x squared. Your y equals x squared, it's something like this. And your x, it runs from 0 to 1. So here your x is from 0 to 1. So you have this. This is the 0. This is the 1. Okay? And then y equals negative x. From 0 to 1, the graph is somewhere here. Okay? The graph is going down here. So of course, this is your negative 1. This is your positive 1. So you are integrating from negative x to x squared. It means your strips will be this. Okay. And then this strip will move from 0 until 1. Correct? So your region is actually this part here. This is the domain of your integration. Okay? So of course, suppose you want to do dx dy. Obviously, you will see if you do that, you will have to do this into two parts, or you will have to divide into two parts. The first part will be here. So it will be from this up to this. Okay. If above the x-axis, if below the x-axis, it will be from the line y equals x to x equals or y equals negative x to x equals 1. Okay. So imagine how these strips move. So anyway, this is easier in a sense. In this order, it is easier because it's just, you don't have to divide into two parts. So we start integrating with respect to y first. So if we do that, we will have y cubed over 3, and x is constant. That's why you have your x here. And you evaluate from y equals negative x to y equals x squared. So if we evaluate this, we will end up with this expression, x to the 7 over 3 plus x to the 4 over 3. Of course, you have here y equals x squared. So x squared cubed, that's x to the 6 times x here, that's x to the 7. On the other hand, y equals negative x, y cubed, it becomes negative x cubed times x here, that's negative x to the 4. But you have minus, so that becomes positive. Okay? And then we now integrate with respect to x. We'll now have x to the 8 over 24 plus x to the 5 over 15. And then we evaluate this as at x equals 0 and at x equals 1. We have 13 over 120. Okay? Questions? Okay. Now, for this problem, we want to evaluate integral from 0 to 2, integral from y over 2 up to 1, cosine of x squared dx dy. Now look at this. Your integrand, that's cosine x squared. It's simply cosine x squared. And in here, you are integrating with respect to x first. But notice, this is not integrable, at least as of the moment. In a sense, we don't know how to integrate cosine x squared dx. We're lucky, this is, integral, double integrals, dx dy. So maybe we can change the order. In fact, that's what we're going to do. Notice that there's no y in here. So if we start with y first, maybe there will be something that will come out that will help us integrate cosine x squared. Okay? So let's look at the region. Okay, let's look at the region. We have here x-axis, y-axis, and then the value of y, the interval, it's from 0 to 2. So the interval, it's from 0 to 2. That's the value of y. So it is 0 here. And then this is 2 here. Say this is 1. And then this is 1 for x. This is 2 for x. And then look at this. For the values of x, you have x equals 1, y over 2 until x equals 1. And of course, your y, it's from 0 to 1. So if you look at this line here, x equals y over 2, we can change this into y equals 2x. Okay? But anyway, x equals y over 2 and your y runs, your y runs from 0 to 2. So this means that your x here will run from 0 to 1. Correct? So the line y equals 2x, it will be this line here. Okay? So let's just continue that one. This is your line y equals 2x or x equals y over 2. Okay? And then until x equals 1. This is your x equals 1. Okay? So let's draw that line x equals 1. So this is your line x equals 1. So what does this mean? With respect to x, the x will run from the line x equals y over 2. Okay? From the line y over 2 until x equals 1. So this is the strip. And then this strip will move along the y-axis from 0 to 2. So this strip will move going up there, going down here. So it means the region of integration will be this. Okay? Okay? So now we have identified the region of integration. We will now change the order of integration. So from integral from 0 to 2, integral from y over 2 up to 1, cosine x squared dx dy, we want to change this. We have still the double integral, still have cosine x squared, but this time we want dy over dx. Because at least we will be able to integrate this regardless of the resulting region. Because at this point here, we cannot do anything. Okay? So, this is our region. This is our region here. If we move our y, okay, if we move our y, it will mean that we need a vertical strip. In this region here, we need this strip here. Correct? We will need this strip here. So, with this same region, okay, let me copy. And then I'll try to erase that strip there. So this is our part here. Okay. So this time we want vertical strips. So for the vertical strip, we have this. We need our y to move from this bottom here until that line there. Okay. So the lower part here, it's always y equals 0. The upper part, it's always the line y equals 2x. So in here, we will have y equals 0 until y equals 2x. Okay? And then this blue strip here will move along the x. It's just from 0 until 1. So in here, we will have 0 until 1. So x equals 0 until x equals 1. Okay? So notice, this doesn't have any y. It's just x. So if we integrate with respect to y, this remains constant. So if we do that, now we will have the integral from 0 to 1. We will have y cosine x squared evaluated from y equals 0 until y equals 2x. Then we close the parentheses and then we have the dx. So if we evaluate this, we will end up with the integral from 0 to 1 of 2x cosine x squared dx. And now we have 2x cosine x squared. We want to integrate that, and that's easily integrable. Simple u substitution. We let u be equal to cosine, or we let u be equal to x squared. Du will be 2x dx. Correct? So if we integrate this, we'll just have sine x squared. Then we evaluate this from x equals 0 until x equals 1. So the final answer here, it's just sine 1 minus sine 0. But sine 0, that's equal to 0. So this is our final answer. Okay? Questions? Okay. So I hope you got the changing of integration or of the variable integration. It's not Fubini. It's not Fubini. Fubini, it's for rectangular region. You can just interchange that without harm. In here, if you try to interchange the variables of integration, you also need to change something in the limits of integration. Okay. For my last problem for this session, so evaluate integral from 0 to 1, integral from 4x to the 4, e raised to negative y squared dy dx. Now you look at this, your integrand, it's e raised to negative y squared. And then you are integrating with respect to y first. And then just like the previous problem, this is not easily integrable. We cannot integrate this using the techniques we have learned so far. But maybe if we do the change, if we change the order of integration, maybe something good will happen. So in order to do that, change, let's try to sketch the region or for the domain. So this is for x, this is for y. So for x, it's just from 0 to 1. So this is 0 here, and then say this is 1 here. And then for y, we need 4x until 4. And for the 4x, when x equals 0, this means we got the lowest to be the 0. So it means we will need y equals 0 until y equals 4. So let me just extend this. And then let me adjust this one in here. So anyway, say this is your 1. So this is 1, 2, 3, 4. So this is the 4 for the y. But you also need what? Y equals 4x until y equals 4. And then your x is from 0 to 1. But y equals 4x when x from 0 to 1, you just have the line. This is the highest point of that line, and then you have this line here. So if you look at this is your y equals 4x. But your y, look at this, the limits of integration. The lower limit, it's 4x. Okay? And the upper limit, it's y equals 4. So for the upper limit, you have this line here. So that line, it's your y equals 4. So lower limit of integration is 4x. The upper limit, it's 4. Therefore, the strip, the vertical strip will be something like this. And this vertical strip will move, okay, along the x-axis from 0 to 1, which means that, let me copy this first. Let me copy this first before I continue with the drawing. So I'll paste it here. It will be used for later. So in here, like I said, in the current arrangement, we will have this strip, okay? And then this strip will move from left to right, from 0 to 1. And therefore, the region is this part here. Okay? If we change the order of integration, it means we integrate with respect to x first. It means we need now horizontal strip. So we still have this region here. Okay, this is our domain. But this time, our strip, we start with the x. That will be horizontal. And then, of course, this horizontal strip will move upwards and downwards from 0 until 4. And therefore, the integral will be, so you have the original integral here from 0 to 1, 4x up to 4, e to the negative y squared dy dx. This will be the integral, this time from 0 to 4. Okay? And then here you will have from 0 to y over 4. Correct? So for the x, it will be x equals 0 until this line, y equals 4x. But you need to write this guy here as x equals y over 4. And same integrand, e to the negative y squared, the order becomes dx dy. And now this is easily integrable. Okay? So for this, we have integral from 0 to 4. And then you will have x e to the negative y squared. We evaluate this from x equals 0 until x equals y over 4. Okay? And then that's your outer dy. So we will have 0 to 4 here. And then we'll have y over 4 e to the negative y squared. And then we have the dy. And in here, again, it's easily integrable. Okay? It's just simple substitution. So you can let u be equal to negative y squared. Du will be negative 2y. Okay? So what will you get? But anyway, I'll leave this here. Try to evaluate this, and whatever you get, if all your evaluation is correct, then that will be the final answer.